All right, so I want to look at an example with you of a piecewise defined function. This function is particularly important in electrical engineering. It's called the Heaviside function. Hopefully I'm pronouncing that correct. And we define it to be 0 whenever the input is less than 0 and 1 whenever the input is greater than or equal to 0. A lot of times with these functions, if you can just sketch a quick graph, it really helps you understand what's going on. So let's do that together. So whenever I'm bigger than or equal to 0, my value is 1, so the function looks like that. And then I've got a hole at 0, and whenever I'm less than or equal to 0, I'm just 0. So that's what it looks like. And so it's pretty easy to see. If you compute a limit anywhere here, as x goes to your point, the function goes to, well, the y value is just 1. So the limits are all clear everywhere except, you guessed it, right here at 0. And so it's hopefully, you can see that if we look at the limit as t goes to 0 of this function h of t, there is no single number that the function is getting closer and closer to as t goes to 0. If you go to 0 from this way, the function is getting closer and closer to, well, it's always 1. If you go to 0 from this way, the function is getting closer and closer, i.e. it's always 0. So those are different. There is no single number that you're closing in on. And so this limit as t goes to 0 does not exist. But think with me. If I just go to 0 from this side, from the right-hand side, then the limit is just 1. The y value is not, it's getting closer and closer to 1 because it is 1. And if I go to 0 from the left-hand side, then the limit is 0 because the function is not just getting closer and closer to 0, it is 0. And so that really raises an interesting issue that we want to talk about. So I'm going to introduce to you one-sided limits. So we write the same notation as before. Limit as x goes to a of f of x equals L. The difference is I put a little minus sign above the a, and that means x goes to a from the left. We write this to indicate that I'm only going to a from the left side. Here's a, I'm coming from the left. Same thing, f gets closer and closer and closer to L as x gets closer and closer to a. You're coming from the left, so you're always less than a on the number line. And then similarly, we can define the limit as x goes to a from the right. The plus here means from the right. So here's a, you're coming down. A is always less than x. X is always greater than a. Okay, so if we go back to our previous example, I already wrote it down, sadly, but it's what we said. The limit as t goes to 0 from the left is 0, and then the limit as t goes to 0 of h of t from the right is 1. So that brings up a very natural question, and the question is, how do one-sided limits relate to regular limits? When I say regular limits, I mean full limits, limits where you're considering both sides at the same time. And well, we have the following proposition. So a proposition is just a mathematical fact. Basically, the really special propositions are called theorems. Sort of your standard, hardworking, everyday mathematical fact is called a proposition. And you can have lemmas, which are sort of baby mathematical facts, and corollaries are sort of the offspring of fancy theorems. But when you see words like proposition, theorem, lemma, corollary, they're all just telling you this is a truth that you can count on. The real joy of doing math is that you don't have to sort of take my word for anything. You can prove it and see and understand it yourself. But at this level of a course, you are going to have to take some things for granted. And so one of them is this. Turns out that the limit as x goes to a of f of x equals L. That happens if and only if the limit as x goes to a from the left of f of x is L, and the limit as x goes to a from the right of f of x is L. And I would challenge you, if you have a minute, stop the video and think about why this is true. You may not be able to prove it, but you can at least get a real clear sense of why it's true. And actually, you probably could prove it if you thought about it. So take a minute, think about that, and then let's go on and end this video with an example. So the example that I want to look at is this function, and I would actually challenge you to pause the video and see if you can figure out what these different limits are. So I want to study the limit as x goes to 2 from the left of g of x. So here's 2. I'm coming to, x is going to 2 from the left. The function g is getting, as x goes to 2, g is getting closer and closer and closer to this y value, which is 2. So this one is 2. As x goes to 2 from the right, so I'm coming in like this, the function is, let's start here, getting closer and closer and closer to this y value. It's coming down to that y value, which is 1. So the limit as x goes to 2 from the right of g of x, is 1. And therefore, because these are not the same, we know that the limit as x goes to 2 of g of x simply does not exist. All right, let's do the limit as x goes to 5 from the right. So 1, 2, 3, 4. Oh, that's supposed to be a 5 there. Whoops. Let's see. Let's clean that up a little bit. There's my 5. Wow, yeah. I should have done a better job labeling my spacing, but whatever. So this is 5, 1. Let's just label them 1, 2, 3, 4, and let's make it 4.5. I can't live with it being spaced so bad. And those are all messy now too. Wow, this is a disaster. 4.5. 4.5, 4.5. Okay, so let's go from the left. We're going into 4.5 from the left. G is getting closer and closer and closer to, you can see 2. So this one is 2. X goes to 4.5. Let's make that from the right. And the same thing, the function is getting closer and closer and closer to this y value again, which is 2. And so therefore, you know now that the limit as x goes to 4.5 in general of the function is just 2. And you can see that because it doesn't matter which side you come from, you're getting closer and closer to this y value of 2. All right, well, we'll end the video here. That's everything for 1.3. Great job. And we'll continue 1.4 soon.